So, as is the case in everything we looked at with atomic absorption and emission spectra, there were specific frequencies that were absorbed or emitted by different atoms, allowing you to distinguish between them. With our infrared spectroscopy, different bonds absorbed at different wave numbers, allowing us to distinguish between them. Same idea for NMR. This is from your the WJEC A-level chemistry data book. There are diagnostic shifts of different carbons. So you can see here boring old hydrocarbon ones between about 5 and 40. Throw on a halogen, you get the shift a little bit higher. Put in some oxygens or nitrogens and you make them a little bit higher, and so on. Generally, as we look at this, the more electronegative that the atoms are that are bonded to the carbon, the nucleus is then less shielded by electrons. If you've got this oxygen bonding to a carbon, that's oxygen's pulling electrons away from the carbon. There's less electron density around the carbon. We say it is less shielded by the electrons. If it's less shielded by the electrons, then you don't need as big a frequency to flip the nuclei. You're not having those nuclei feeling the magnetic field reduced by as many electrons. It's less shielded. Okay, and there's a smaller energy gap. So we see as we go down, there's some halogens, oxygens, nitrogens, oxygens, nitrogens. You have this double bonding and then the benzene ring, because again the carbon nuclei are actually got less electron density because there's more electron density between the atoms in that pi cloud. Okay, now if I'm just going to go through quite a few spectra here just to show you different things, different shifts, different groups. So if we go back to propanol, okay, what do we have in propanol? Well, we have a carbon that is bonded directly to an oxygen. That peak there is the carbon directly bonded to an oxygen. Such carbons you would expect to have a shift at about 50 to 90 parts per million. This one down here is at about 63 parts per million. Okay, now then these two carbons here, they're relatively boring. Okay, they're not bonded to anything except hydrogens or other carbons, and so they would be in that 5 to 40 range. There you go, 5's about here, 40 up here, so they sit nicely in there. Now of course, as I pointed out on the very first slide, and we'll emphasize again here, this carbon here isn't bonded directly to the oxygen, but it's closer to the oxygen than this carbon is, and so we see that it is more downfield, as it says. It is more less shielded than this one is, because that oxygen is still pulling electrons away, and this one of course feels it the most, this one feels it second most, this one feels it third most. Next example, 1-bromobutane. So here's 1, 2, 3, 4 carbon atoms with the first one bonded to the bromine. Bromine, of course, more electronegative than carbon, sucking electron density away from that carbon. That carbon has less electron density around it, thus it is less shielded by electrons. Therefore, it's going to be further away from the standard, further downfield. It needs less of a frequency to make it absorb, and that's it right here, because it's got less electron density thanks to the bromine sucking that electron density away. And we see that we expect a chloroalkane or a bromoalkane to absorb somewhere between 10 and 70 parts per million. This one here is at about 53 parts per million, so there it is right there. Now, I'm not going to dwell overly on this, but do notice that the bromine has an effect more than just the first carbon. It's sucking electron density away from this carbon, which means it would like to suck a little bit away from this carbon, which means it would like to suck a little bit less from this carbon, and probably down here, this carbon doesn't even know the bromine exists. And you can see that the peaks go more upfield as you get more shielding, because there is less of the effect on the bromine. So I would say this peak here, very definitely the one bonded to the bromine, the next carbon this one, the next one that one, and the next one that one. Another example, let's look at benzene. When you think of benzene, each of those carbon atoms is identical. Okay, and so you're only going to see one signal in the carbon NMR. You expect benzene aromatic rings to come between 110 and 160, and that's very de-shielded downfield because you've got that big pi cloud in here that's sucking the electron density into the pi cloud, affecting therefore the carbon atoms less shielding on the carbon atoms, more downfield, further away from the standard. Okay, so we can see it right there. Our value actually about what, at 128, 129, nicely in that range for aromatics. For our last examples of carbon-12, and of course there'll be worksheets, there'll be quizzes, there'll be all kinds of fun things, I'm going to dwell on compounds that contain oxygen. Just like the infrared, this is something that the A-level boards particularly like. So compounds containing oxygen. And you can see we've got all kinds of oxygen in here. We can have carbon single bonded to oxygen, as you'd see in alcohols or in ethers. We haven't talked much about ethers. You can see we've got carbons double bonded to oxygen, as we'd see with the carboxylic acids, and then higher up the aldehydes and the ketones. And you can see that double bond, carbon double bond O, doesn't just affect the carbon that is double bonded to the oxygen, but we get a special extra little entry in this table for a carbon that is bonded to the carbon that is double bonded to the oxygen. So let's look at a nice simple example. Acetone here, propanone, however you want to say it. And when you look at this, there are two types of carbon in here. There's the carbon that's double bonded to the oxygen, and then there's the carbon in the methyl groups that are bonded to that carbon that's bonded to the oxygen. So what would we expect to see? Well, the carbon bonded to the carbon there correspond nicely to this picture right here, somewhere between 20 and 50, and we see them there smack in there at 30. But then of course the beautiful one, the one that's really affected, the carbon's really affected by this oxygen, all the way down there at greater than 200 ppm, as you'd expect, somewhere between 190 and 220. Okay, so a nice diagnostic test here. Here's that carbon-oxygen double bond, just like, of course, with the infrared, carbon-oxygen double bond stands out like a sore thumb. It's got such a high chemical shift. And then the carbons bonded to the carbon bonded to the oxygen in acetone, both of those carbons, whether you call them carbon 1 or carbon 3, they're identical, so they will give you one shift. I haven't dwelled too much on the idea of identical atoms, just giving you one peek. There's practice on that in the quizzes. We'll practice on that on the worksheets as well. And of course, we'll keep referring to it as a concept all the way through. Next example, let's look at a ester. Okay, right here, we expect one between 160 and 185. We have methyl acetate, and so you've got two methyl groups here, the pink and the green, but they're very distinct as methyl groups. This methyl group is bonded to a carbon that's a double bond oxygen. This methyl group is just bonded to an oxygen itself. So when we think about what's in there, okay, the various bits we've got the pink one right here between about 20 and 50. We've got the green one here between about 50 and 90, carbon single bonded to an oxygen. And then of course we have the blue one, the carbon double bonded to an oxygen. Have a look at the spectrum. There are exactly what we're expecting. There's the blue one there up at about 172, smack in the middle of where we would expect an ester. There's the carbon bonded to the oxygen there right at about 50, down the sort of low end of that. And then finally here's the pink one that is bonded to a carbon that's bonded to that double bond O, coming in smack at 20 right there. Finally, let's think about a fun A-level type question. Got molecule that we know is C4H8O. We know its empirical formula. We know from infrared that there is a carbon-oxygen double bond in there, but we don't know which of the three isomers it might be. Is it butanol? Is it butanone? Or is it 2-methyl propanol? Well, let's think before we look at the spectra, the possible spectra, what would we expect to see from these three different compounds in the carbon-13 NMR? Well, we've got three distinct type of carbon atoms in there. okay, which I've highlighted here or circled or rectangled or whatever you want. Most important is, of course, the aldehyde ketone one, as I've done in green, the carbon-oxygen double bond, the carbon that is attached, double bonded to the oxygen. So that's that carbon, and that carbon. And then, of course, we have the sort of nice blue here. That's the carbon next to the carbon that's double bonded to the oxygen, carbon next to the carbonyl carbon. And then we're going to have other just regular old carbons that are a bit further on. So we got green, we got blue, and we got pink possible carbons. The green in 190 to 220. The blue will be the ones that have peaks in 20 to 50, and then the pink somewhere between 5 and 40. So let's look at this first one here. There's 4 carbons, 1, 2, 3, 4. Well, carbon 1 is the one that's the carbonyl carbon double bonded to the oxygen, so we'd expect that to be in the 190 to 220 region. Carbon 2 is one of the blue ones. It's a carbon bonded to the carbonyl carbon. Carbon bonded to the carbonyl carbon, so we would expect that to have a peak at about 20 to 50 parts per million, so 1 peak there. And then 3 and 4, they're really too far away from this carbonyl carbon for us to say that they fall into this range, so they're just going to be in the pink range. I would expect, of course, carbon 3 to feel the effects of the oxygen more than carbon 4, but we'll put both of those in that pink region. So 2 peaks in the pink region, 1 in the blue and 1 in the green for butanal. Now let's go for butanone. Label the carbons. Well, the first one, we've got carbon 2 is of course a carbonyl carbon, so that will be in the 190 to 220. But now that's the carbonyl carbon. What's bonded to that? What's in the blue region, right? Carbon bonded to the carbonyl compound carbon, and that is of course both 1 and 3 are going to be bonded to that carbonyl carbon. So we should expect to see 2 peaks between 20 and 50. And then finally 4, while of course it's going to feel the effect of the oxygen, it's too far away for us to put it in anything other than the pink category. Finally, looking at 2-methyl propanol down here, let's label the carbons, 1, 2, 3. And now notice again, there is carbon 1 here, very distinctive, double bonded to the oxygen. Carbon 2, bonded to the carbonyl carbon, but now this carbon here and this carbon here are identical carbons. They're just CH3 groups bonded to carbon 2. So we got 2 carbon 3s, carbon 2 and carbon 1. Carbon 1, of course, is the carbonyl carbon. It's going to be in the green region. Carbon 2 is the one bonded to the carbonyl compound, so that's going to be in the blue region. So 1 peak in each of those. And then, of course, carbon 3 is just a regular old pink carbon, but they're the same carbons, so we'll only see 1 peak in the carbon pink region. Both of those, both carbon 3s are identical carbons, so therefore we'll just see the 1 peak. So you can see, as we even think about it, without looking at the spectra, that we should be able to use NMR to distinguish these 3 isomers. Now, unfortunately, I experimented with how to put all this on one particular page, keeping it nice and sensible, and it wasn't a good way to do it that didn't lose all kind of format, but we'll just think about as we go through. But essentially what we're going to do is we're going to have 2 compounds that have got 4 peaks, 1 compound that's got 3 peaks, so that's going to be easy to identify immediately. And then what should we see for the ones that have 4 peaks? We should see a peak and then 2 close together versus a peak and then 2 close together and then a peak. Let's see, shall we? Let's take a peek at the spectra. You knew I couldn't resist that. So here are the 3 spectra. Okay, well, what can we see here? Well, immediately we can see we got 4 peaks, and 3 peaks. So the 3 peak one must correspond to the 2-methyl propanol. That's compound carbon 1 there in the pink region, 2 there in what we would call in the blue region. Sorry, 1 was in the green region, 2 in the blue region, and 3 in the pink region. Now, as we look at these other ones, there's our high green one. There is a peak that is in the blue region. There's 1, 2 together in the pink region versus these 2 in the blue region, this one in the pink region. So that tells us, hopefully, that this first one is going to be butanal. That's where carbon 1 is there. Carbon 2 is the one bonded to the carbonyl, so that's there in what we call the blue region. And then 3 and 4, far enough away from the oxygen, they're not really going to feel the effect. So that's those peaks there. If I had a gun to my head, I'd say that was 3 and that was 4, but nobody's got a gun to my head, so I'm just putting them together. And then obviously this must be butanone. Let's see what those peaks are. Obviously the carbonyl one is our green one. That's the carbonyl carbon, the very high ppm, the very far downfield, the very de-shielded carbon there. 1 and 3 are of course in the blue area because they're both bonded to carbon 2 to the carbonyl compounds, so that would be those two. And again, I'm not going to try and split them up. I wouldn't actually know where really to begin to split them up, so both of these just correspond to 1 and 3. And then poor little 4, it's the only one there in the pink region all the way down there. So hopefully our carbon NMR discussion made a little bit of sense to you. We will do lots of practice, but the important thing to remember is that carbon NMR allows you to distinguish between carbons in different environments in the molecule.